Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at a quick review of some of the concepts, specifically about derivatives and integrals from Math 190 that we'll be needing pretty much right away in our class. So to start off with, we're going to just look at a little table of basic derivatives that you should be very familiar with. Even though, of course, during this class you'll be allowed access to your notes, I would highly recommend having all of these derivatives memorized because a lot of times a single problem might involve doing several of these derivatives all at once, and it makes things tremendously easier if you have everything just sort of right at your fingertips already sort of memorized. So let's talk about the derivatives of some basic functions that you should already sort of know. One other quick thing just sort of in the background as you think about this, remember that when taking a derivative, you start with a function, and when you take the derivative, you end up with another function. So the derivative, for some of you guys that are headed much further down the sort of math line, if you make it to Math 270 at some point, the derivative is an operator, and you input functions, and it outputs functions. So you start with a function, the derivative of a function is another function. So let's look at some of these basic derivatives here. So first one here, if you take the derivative of a constant k with respect to x, so x is our variable, all right, the independent variable, k is some constant, then the derivative of a constant is 0. This guy here is sometimes referenced as like the power rule or something like that, right? X to the n, the derivative of that is nx to the n minus 1. Now, a couple things to keep in mind for this. This rule handles polynomial situations, things like x squared, x cubed, x to the fourth, and so on. But it also handles some rational situations. Remember, something like 1 over x or 1 over x squared can be thought about as x to the negative 1 or x to the negative 2. So this derivative rule will take care of that. This also takes care of some radical situations, right? Things like the square root of x. Square root of x can be thought about as x to the 1/2. So you can use this sort of rule there. So really, this handles x to any exponent, right? You have x to an exponent, you can use this rule, nx n minus 1 as the derivative. Then we've got a couple rules here about exponential functions. So the derivative of e to the x is e to the x. Again, for some of you guys, as you sort of take more and more math classes, you'll find that, this property that e to the x is a function that has itself as its derivative is actually an alternate definition for the exponential function. You guys probably also learned a limit definition for e, as the limit as n goes to infinity of 1 plus 1 over n to the n. But another alternate definition of the exponential is it's a function who has itself as its derivative. What happens if you don't have the natural base e, so instead you have a function a to the x? Well, then the derivative is ln of a times a to the x. Technically, we could have just crossed this rule out and only wrote this one down because this guy is the more general rule. Keep in mind that if a is equal to e, then this would be ln of e, e to the x, but ln of e is 1, so it would just reduce to e to the x. The only reason we take the time to write out both of them separately is because e to the x shows up so frequently, and it has such a nice clean rule that we just might as well keep it separate there. All right, let's zoom in a little bit more because the table's a little bit messy here, but for the natural log of x, the derivative of the natural log is 1 over x. If you have a non-natural log, so log base b of x, you use the same approach. So you have 1 over x, but you also get a factor of ln of b in the denominator, right? So the difference here between that a to the x and that log bx formula is that in a to the x, that factor of ln of the base ends up as a multiplier, whereas here the ln of the base ends up in the denominator. Now we're going to turn our attention to 6 trigonometric derivatives. Derivative of sine is cosine. Derivative of cosine is negative sine. So as you guys know, if you keep differentiating sine and cosine, they just keep going around in a pattern. Derivative of sine is cosine. Derivative of cosine is negative sine, so on and so forth. For the derivative of tangent of x, you get secant squared. Derivative of cotangent, whenever you're doing the co-functions, you sort of get the co of the derivative, but with a negative sign. So the derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent, and the derivative of cosecant then is negative cosecant cotangent. And then lastly, we have a couple derivatives of some arc functions. Just out of convenience, we usually focus on the arc trigonometric functions, not the arc co-functions. So you'll notice that we have arcsine, arctangent, and arcsecant here, and we're sort of ignoring arccos, arccotangent, and arccosecant. You might know those derivatives as well, and that's great. We're not going to run into them very frequently, so these three are the ones that you really want to make sure you know. Derivative of arcsine is 1 over the square root of 1 minus x squared. Derivative of arctangent is 1 over 1 plus x squared. And the derivative of arcsecant is 1 over 1 over absolute value of x times the square root of x squared minus 1. A couple little things. Some of these are really interesting, so I just want to take a moment to mention a couple things here. One, notice that in the two that have radicals, these radicals relate directly to the domains. As you guys know, the domain of arcsine is the range of sine. The range of sine is -1 to 1, so the domain of arcsine is -1 to 1. And notice that this square root here, square root 1 minus x squared, only makes sense from -1 to 1. So if you go outside of -1 to 1, you're square rooting a negative number, you're getting a imaginary or complex denominator, doesn't make any sense. And that corresponds directly to the domain of that arcsine function. Same thing with arcsecant. Domain of arcsecant is the same as the range of secant. Range of secant is -infinity to -1, union 1 to infinity. And notice that that makes sense right here. Only things that make sense in that square root of x squared minus 1 is if x is bigger than 1 in absolute value. So again, this square root there, it actually corresponds directly with the domain of these arc trigonometric functions. Also, want to call you guys' attention in arcsecant. Formally, this guy should be an absolute value of x here. Oftentimes, if you glance at just like a resource, you'll just see x here. It's not the biggest deal if you forget the absolute value. Technically, it is an absolute value. That is absolutely correct. A lot of times, though, when you're working with arcsecant, you're only working in positive x, though. So the absolute value is not so important there. But if we're being really formal, the derivative of arcsecant does have that absolute value of x there. Lastly, I'd like to call attention to arctangent. Arctangent of x is one of my favorite functions, and we'll see it very frequently. Arctangent has a lot of very interesting properties. Keep in mind, arctangent is an example of a function that has a full domain, -infinity to infinity, but a limited range. It has two different horizontal asymptotes at -pi/2 and pi/2. So those are interesting properties in of itself. And it has an incredibly unique property right here as we're talking about functions and their derivatives. Notice that as a function, arctangent is an inverse trigonometric function, yet its derivative is a rational function. And that is pretty unique. There's not a lot of functions out there that when you take their derivative, they change the type of function so radically. I mean, we're going from an inverse trigonometric function to something that is much, much more mellow, much more mild, just a rational function. So very interesting. We'll encounter arctangent many times throughout our course. So this right here just gives us a list of basic functions and their corresponding derivatives. Along with your guys' study of functions and derivatives, you also probably learned a number of derivative rules, right? What to do when you have these things that are having operations between them, addition, subtraction, multiplication, division. So let's talk about those derivative rules as well. So for the derivative rules, probably these are the 5 main ones that you guys have encountered. Things like the constant multiplication rule, which basically says that the derivative of a constant times a function is the constant times the derivative. In other words, the derivative distributes through constant multiplication. That's what this is really saying. And then there's the addition rule that says that the derivative of a sum of two functions, so the derivative of f of x plus g of x, is equal to the derivative of f of x plus the derivative of g of x. In other words, the derivative distributes over addition. Now, of course, you can put these two together and derive what's called the subtraction rule, because, of course, subtraction is just addition with a -1 multiplier here. So we don't really need to say the subtraction rule separately. It's just a natural consequence of these two rules. Again, just out of interest, for some of you guys, if you go further on, and again, you take something like Math 270, you learn about differential equations and differential operators. These two things here actually are referenced as making the derivative linear. Right? The derivative is a linear operator because it distributes over constant multiplication and it distributes over addition. Is that really relevant for our class? Not so much right now, but just something to keep in the back of your head. There's also these rules about how the derivative interacts with things like products and quotients. So this is the product rule. The derivative of the product f of x times g of x is f prime of x plus f of x times g prime of x. Apologize for the interruption there. Don't quite know why that came through. Should have all been silenced, but that's okay, right? We're just starting off. So f of x g of x prime is f prime of x g of x plus f of x g prime of x. So that's our product rule there. There's the quotient rule. The quotient rule says that the derivative of a quotient, f of x over g of x prime, is f prime of x times g of x minus f of x g prime of x over g of x squared. In the product rule, do keep in mind that the order doesn't really matter because this is a plus, and plus is a commutative operation, so it doesn't really matter which one you do first. Here, though, the order does matter. You need to differentiate the numerator first, then multiply with the denominator, and then subtract, since subtraction is a non-commutative operation. So the order in this formula really matters. Lastly, maybe the most important derivative rule you guys learned, which is how to deal with the derivative of compositions. Remember, composition is a really unique operation. It's an operation that only makes sense for functions, as opposed to, things like addition, multiplication, division. That makes sense for numbers, but composition is special for just functions. And the chain rule tells us how to work with derivatives of compositions. So the derivative of a composition, f of g of x, is f prime of g of x times g prime of x. In other words, you differentiate the outer function and then input the inner function times the derivative of the inner function. So these rules, combined with that table of basic derivatives, allows us to basically differentiate almost any function we encounter. Taking derivatives, while maybe sometimes messy or sort of detail-oriented, is always going to be doable, right? You have a giant list of derivatives you have all these rules that tell us how to deal with any operation that might be sort of combining functions together. So we can pretty much take the derivative of any function we encounter. Real quick, before we change gears and start talking about integration or anti-differentiation, let's go ahead and just take a quick look at a couple examples here. So here's a couple functions. We're just going to try to determine the derivatives of each of these. So for the first one here, we've got f of x is x cubed minus 3x plus 6 cosine 7x. So for a here, right, if we have f of x is x cubed minus 3x plus 6 cosine 7x, should be very easy to take the derivative here. We have 3 separate terms in each of these, so we just take the derivative of each of these separately, right? That's the addition and subtraction and the constant multiplication rule sort of being all put together there. We just need to take the derivative of each of these separately. That derivative of that x cubed there, that becomes 3x squared. That's that x to the n is nxn minus 1. The derivative here of minus 3x, well, this is an x to the 1. That 1 drops down, doesn't change anything there. And then, of course, it would be x to the 0. So no x's would remain. So just minus 3. And then here, we should be a little bit careful. There is a composition. So we're going to be technically doing a chain rule. The derivative of cosine is going to be negative sine. So we get negative 6 sine 7x. And then we get the derivative of the inside, which is times 7. After a brief simplification, we can get this as 3x squared minus 3 minus 42 sine 7x. And there we go. This guy just basically used some of that addition constant multiplication rule. Notice we use the constant multiplication rule here where we basically just take the derivative of this and left the 6 alone. And of course, then we use chain rule to deal with this component. Let's go ahead and take a look at B as well. So B, we've got g of x is arctan of x cubed. So when we go to do g prime, we're going to be using chain rule. The derivative of arctangent is 1 over 1 plus x squared. But of course, this is going to be going inside of that. So we're going to be getting 1 plus x cubed squared. And then times the derivative of the inside there, which of course would be 3x squared. After a brief simplification, we should be able to get that as 1 over, no, we don't need to say 1 over, we can just pop that 3x squared up top, 3x squared, 1 over, 3x squared, 1 plus x to the 6 there. So we get 3x squared over 1 plus x to the 6. All right, last one then. You got C there. We have h of x, which is equal to e to the 3x over tan 2x plus 1. Notice we can clearly see that we're going to have to use quotient rule here because we have a fractional expression. Also notice that we'll have chain rules whenever we differentiate e to the 3x and tan 2x there. So h prime here, we've got to differentiate the numerator first. We're going to get e to the 3x, but then the derivative of the inside is going to be 3. So it looks like we should get 3e to the 3x. Then times the denominator, but untouched, so tan 2x plus 1. And then minus, we'll leave the numerator alone, so e to the 3x. And then we'll differentiate the denominator. Differentiating that tangent is going to give us a secant squared 2x. But of course, we'll have to take the derivative of the inside, which is going to be 2. And then, of course, the derivative of that plus 1 is going to be 0. So we'll have a plus 0 there. Don't need to write that. So we can just close up our parentheses. Then we can put our denominator and square what was originally there, tan 2x plus 1 squared. Doesn't really look like there's much simplification. I suppose the only nice thing to do is move that 2 in front. So we can say h prime of x is 3e to the 3x tan 2x plus 1 minus 2e to the 3x secant squared 2x over tan 2x plus 1 all squared. We could try to multiply this out and see if there's anything else, but it should be very clear that there aren't going to be really any other simplifications, so might as well just leave it here. So there's a couple quick examples of just taking some derivatives. Let's change gears now and talk a little bit about antidifferentiation or performing integrals. So integrals. Integrating is definitely a lot more challenging than taking derivatives. A lot of the stuff we're going to be doing at the beginning of our class of Math 191 is going to be learning about techniques of integration. And one of the fundamental differences that we're really going to call attention to is that with derivatives, any function out there, no matter how messy it is, if we're sort of careful and we use the appropriate rules in the appropriate order, we can take the derivative of. But for integration, that's simply not the case. There are actually very basic functions out there that have no closed form for their antiderivative, meaning that there's no single expression, single basic functional expression that says what their antiderivative is. We'll learn some ways of coming up with their antiderivatives that aren't closed form expressions, but taking integrals or performing antidifferentiation is a much more challenging task than differentiation. So, to start off our discussion, let's look at a basic list of indefinite integrals or antiderivatives that we should know. Before we do this, though, I do want to talk a little bit about the result of an indefinite integral. Do keep in mind here that when we take an indefinite integral, we take the indefinite integral of a function, and the output, or what we return, is a family of functions. When you're taking an indefinite integral, you always add a constant of integration, which means that the result of an indefinite integral is not another function, but it's an entire family of functions. So it's very different than differentiation. When you differentiate a function, you get another function. But when you integrate a function, you get an entire family of functions, where every member of that family, if you take its derivative, you get back to what you initially integrated. So let's take a look at some antiderivatives that we should already know here. So if we integrate a constant k with respect to x, we get kx plus c. If you integrate x to the n dx, you get this, which is often referenced as the power rule for integrals, 1 over n plus 1, x to the n plus 1. You sort of remember this as adding 1 to the exponent and then dividing by that new exponent, plus c. Now, this rule right here does not hold if n is negative 1. That would be because the denominator then would become 1 over 0, which is undefined. So this rule works for any n except for n equal to negative 1, meaning it works for whole numbers like 1, 2, 3, 4, 5. It works for negative numbers except for negative 1, so negative 2, negative 3, negative 4, negative 5. But it also works for things like x to the 1/2, like the square root of x. The only time that this power rule does not apply is when n is exactly negative 1. Now keep in mind, if n is negative 1, then you have x to the negative 1, which is the same as 1 over x. So we have specially that the integral of 1 over x dx is actually ln x plus c. Now again, here we should be careful. It's actually ln absolute value x plus c, and we will try to be more careful about this absolute value than we are about the one with the derivative of arcsecant. This absolute value is pretty important here. All right, then we have some integrals of some exponentials. The integral of e to the x dx is e to the x plus c. Makes sense. If the derivative of e to the x is itself, then its integral is also itself, but with that constant of integration. The integral of a to the x dx is 1 over ln a times a to the x plus c. So you get a factor of 1 over ln of a. Notice that that is the reverse of the derivative rule, where the ln of a would be multiplied. Now it ends up in the denominator because the integral is really the antiderivative. Then we have a couple basic trigonometric integrals. Integral of sine x dx is negative cosine x plus c, and the integral of cosine x is sine x plus c. Notice that which one gets the negative is switched here because, again, anti-differentiation, we're going in reverse. Then a couple more tricky ones. Integral of tangent x dx and integral of cotangent x dx. For tangent, it's ln absolute value secant x plus c, and for cotangent, it's an integral of negative ln cosecant x plus c. Now, these ones are a little bit trickier. If you don't remember exactly why these are the case, you actually probably at the very end of your 190 class derive these results using the only technique of integration you've learned so far, which is integration via substitution, or U-substitution. So these guys are actually U-substitutions that are pretty clever, but these are the results here. And for us, once again, these ones should pretty much be memorized here. We don't really want to have to go rederive these results every time we encounter them. Also, do keep in mind that a lot of times when integrating, you get alternate forms that are equivalent. So sometimes you will see this guy referenced as negative ln absolute value cosine x plus c. That is exactly equivalent to this. You might ask yourself why. Well, remember that constants outside of a logarithm can be brought in as exponents. If you bring that up as an exponent, you end up with cosine x to the negative 1. And what is cosine x to the negative 1? Well, it's 1 over cosine x, which is exactly secant. So this and this are the equivalent expressions for that integral there. Same thing here. You might often see this guy referenced as ln absolute value sine x plus c. Same trick here. You can bring that negative inside, right? You get cosecant x to the negative 1. That's 1 over cosecant, which is equivalent to sine there. So just a couple equivalent expressions here. That also just lets you guys know that when integrating, there's sometimes many forms that are actually equivalent functions. Sometimes you guys might be integrating a function, get an answer that looks different than maybe the solutions or what somebody else got, but they could be the same function, just sort of hidden up. You gotta sort of be able to look at these algebraic manipulations and determine if they're really the same function. Then we have a couple weird ones here. Integral of secant squared and integral of cosecant squared, tangent x plus c and negative cotangent x plus c respectively. Why are we talking about integrals of secant squared and cosecant squared? Well, we are talking about these because these are basically just reversing derivative rules. We know that the derivative of tangent is secant squared, and we know the derivative of cotangent is negative cosecant squared. So since we have a derivative rule, or a known derivative, we can very easily reverse that. So you guys might not have actually seen yet how to integrate secant and cosecant. We'll actually talk about those a little bit later on in our class, but right now it's actually a little bit easier to integrate secant and cosecant squared because we can just reverse those derivative rules there. Then you've got these guys here, integral of secant x tangent x dx, that's secant x plus c, and integral of cosecant x cotangent x dx, that's negative cosecant x plus c. Those guys, again, just reversing some known derivatives. Then finally, we have all these, which are reversing each of the inverse trigonometric function derivatives. So the integral of 1 over root 1 minus x squared, that's arcsine x plus c. Integral 1 over 1 plus x squared dx, that's arctangent x plus c. And the integral of 1 over x root x squared minus 1 dx is arcsecant of c. And you'll notice I even dropped the absolute value here because, again, it's not going to be a big concern for us in our class then. So this is a short list of indefinite integrals that you guys have learned. There are a couple conspicuously missing functions here, some basic functions that you guys probably haven't learned the integral of yet. A main one is, what is the integral of ln x dx? Ln x is a very basic function. We know its derivative is 1 over x, but we actually don't know yet how to integrate it. We'll learn that very soon, though. As soon as we get into Chapter 7 and learn our next technique of integration, then we'll be able to actually go ahead and integrate something like ln x. You'll notice that we also don't know things like how to integrate arctan of x dx, and you might not even have yet seen how to integrate something like secant x dx, right? So there are some basic functions that we don't have nice, clean integral formulas for yet, and there will be some basic functions out there that we can't even get nice closed forms for. So again, integration, very different procedure than differentiation. Are there rules for integration? Well, there are a couple integration rules as well as some relations between integration and differentiation. So let's go ahead and talk about those as well. So, integral rules and techniques that you've encountered thus far. So, constant multiplication rule, the integral of a constant times a function dx is the same as the constant times the integral of the function. So in other words, when integrating, you can pull constants through the integral. You've got the addition rule as well. The integral of a sum is the same as the sum of the integrals. In other words, integrals distribute over addition. Are there product rules and quotient rules for integration? Not really. There's techniques that attempt to reverse them that we'll talk about, but right now these are probably the only two rules you guys have encountered for what are valid manipulations of an integral. You guys have learned one integration technique at the end of 190. You should have encountered U-substitution. The theory behind U-substitution, we'll take a look at in an example or two in just a moment, but the theory behind U-substitution is that it attempts to reverse the chain rule by changing the variable of integration. Generally, we use the letter U for that substitution. Because it attempts to reverse the chain rule, it is very good for integrating compositions of functions. A good tip-off as we go further in this class that you need to use U-substitution is if you see a composition in your integrand. If you see a composition inside the integral, then you pretty much know you need to use U-substitution. There are other situations where you use U-substitution even without composition, but anytime you see composition, U-substitution should jump to the forefront of your mind there. Lastly, we won't use this too much, but we should just remind ourselves, fundamental theorem of calculus, the relationship between derivatives, antiderivatives, also definite integrals. So part one of the fundamental theorem of calculus said that if you have a function, capital F of x, that is the antiderivative of little f of x, in other words, if big F prime of x is equal to little f of x, then the definite integral from a to b of little f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. This part one of the fundamental theorem of calculus basically tells you guys how to handle definite integrals. It says that if you can find any antiderivative of the function, then you just evaluate that antiderivative at the two ends, take the difference, and that is equivalent to the definite integral. Part two of the fundamental theorem actually goes the opposite direction and says that if you differentiate the indefinite integral of a function, you get back to where you started. And this should make sense, right? Because this indefinite integral here gives us a whole family of functions, f of x plus c, that have the property that when you differentiate them, you get back to this. And then, of course, when you have that f of x plus c and you differentiate it, you end up with f prime of x. The c just drops out, and that f prime of x, well, that by definition, it's that little f of x. So two different statements of the fundamental theorem of calculus that relate the derivative, the integral, and the definite integral together. Let's wrap this little review up by just taking a look at a couple examples, making sure we're comfortable doing some basic integrals here. So we're going to try to evaluate the following here. We've got a definite integral here and then three indefinite ones. One thing, again, just in case it's been a little while since you've been integrating or just to really stress the theoretical difference here, keep in mind that the answer to A is a number. When you finish evaluating a definite integral, you are getting a number. Technically, that number represents the area under this curve and above the x-axis on this interval. Here, for the other three, though, all of these are indefinite integrals. They have no bounds, no integration bounds. So the answer to each of these will be a family of functions, meaning we'll get some function plus a constant of integration. So very different, even though they all involve integrals. These three are outputting families of functions. That's the answer we're looking for, whereas this guy is looking actually for a literal number. So for a here, we have the integral from 1 to 2 of 5x to the fourth plus 7 over x minus 12 over x to the 7th dx. Probably a good idea to think about this as 5x to the 4th plus 7 over x. I don't need to bother changing this into a negative exponent because if I did, it would be 7x to the minus 1, which is the one time that that power rule doesn't apply. But then we can think about this guy as minus 12x to the minus 7 dx. And it is worth switching this guy to that negative exponent because that type of negative exponent, negative 7, is the type that the power rule applies to. Now we can go ahead and perform our integration here. This guy is going to be an x to the 5th. We add 1 to the exponent, and then we divide by the new exponent, which is going to remove that 5 there. Here, this is going to become plus 7 ln absolute value x. Here, I'm just thinking about 7 over x as 7 times 1 over x. Then I know I can pull this out and just focus on integrating the 1 over x, which gives me that ln absolute value x. And here, I will get a x to the minus 6, add 1 to the exponent, then divide by that minus 6. Minus 12 divided by minus 6 is going to become plus 2. So this is the antiderivative. No need to put plus c, though, because since this is a definite integral, we just need any single antiderivative, so we might as well use the one with the c being 0. And then we're going to put an evaluation bar, 1 to 2, that says that we need to evaluate this antiderivative at 2 and then evaluate it at 1. So if we go ahead and do that, we can plug in 2, and it looks like we'd get like 32 plus 7 ln of 2, no need for the absolute value there, plus 2 over 64, because 2 to the 6th is 64, and it would be in the denominator because it's a negative exponent. That's evaluating at 2, and then we need to evaluate at 1, so it looks like 1 plus 7 ln 1 plus 2. And then I guess we can do a little bit of simplification. We're going to have minus 1 and 2, so that's going to be a minus 3. I guess I can make that a 29. So it looks like we'd get 29 plus 7 ln of 2 plus 1 over 32. We use this, and of course ln of 1 is 0, so we don't need that either. There we go. Can we go further? I guess sure, we could pull out a calculator and get an approximation for this as a decimal. No need to do that. To be honest, we don't even really need to simplify. If you're doing a definite integral, this would probably be sufficient right here because you've demonstrated that you understand how to plug in those bounds. And that's about all we need there. All right, so let's go ahead and take a look at B. B is going to be an indefinite integral, meaning that we are looking for our result as a family of functions that are all antiderivatives here. All right, we take a look at this. Things look pretty messy in here, right? We've got a composition, we've got a fraction, we've got sine, ln, and x. But we said a magic word there. We mentioned composition. Probably going to need to use U-substitution here. So let's try to do a U-substitution. What are we going to U-sub for? Well, we're going to make use of that composition there. We're going to let U be equal to that ln x. Now, whenever you're doing a substitution, you're substituting out in the integrand, but you also need to take care of the differential, the actual with respect to here. So we can differentiate both sides here, and we get that du is 1 over x dx. Now, from here, people have a lot of different ways of doing it. Some people like to solve for dx and then plug in. I'll go ahead and just do that in this method because it is the most sort of consistent method. So we can say x du is equal to dx, and then we can go ahead and plug in. So what happens here with our substitution? Well, we have sine of u. We didn't really substitute for x, so we're just going to keep that as an x down there. And then this dx now becomes this x du. Now, this step right here is sometimes referenced as sort of an intermediate step. This is not an appropriate form to move forward with because you have two different variables present right now, u and x, and you're only integrating with respect to one of them. So before you actually can integrate here, you have to make sure that the original variable, x in this case, is completely canceled out or completely substituted for. Luckily here, we can see that this works pretty nicely because we can cancel those x's. So this simplifies to sine of u du. Then we can integrate. We should get negative cosine u plus c. And again, if we want to, we can keep track of some equal signs there. That's all good. And if we look at that guy then, well, that's not our final answer. It doesn't make sense to say that the antiderivatives here is a family of functions in a different variable. So we need to resubstitute that u equals ln x in there, negative cosine ln x plus c. And there we go. That gives us our family of antiderivatives. If you differentiate this, you are guaranteed to get this because the plus c will drop out. And if you differentiate this component, you will guaranteed to get that. All right, remember that's also a good comment there. If it's been a little while, you can always check when you're doing indefinite integrals by differentiating your result, and you will have to get back to what you were integrating. All right, let's go ahead and give ourselves another page to wrap up the other ones. So for part C, we need to integrate tangent squared x dx. Now, this is a sort of classic one because if you take a look at this, it doesn't look particularly bad. It's certainly not as crazy as this one, but in some ways, this guy's a little bit trickier. There's not really much of a composition to go off of, and there's not really much else we can do. We know how to integrate tangent, but this is tangent squared, and you can't just bring your integral through the exponent. We know integrals distribute over addition and subtraction. We know they distribute over constant multiplication, but they definitely don't distribute through exponentiation. So we're pretty much stuck here. What we can do, though, is that while we don't know much about integrating tangent squared, we know a lot about integrating secant squared. So we can use a trigonometric identity. We can remember that 1 plus tangent squared x is equivalent to secant squared x, which means that tangent squared x is actually secant squared x minus 1. So if we throw that in there, we get secant squared x minus 1 dx. This looks much better because we know how to integrate this. We know how to integrate this, and they're two separate terms, which we know the integral distributes over. So we just integrate each piece separately. Integral of secant squared, we know that that is tan x. Integral of that minus 1 is going to be minus x, and then plus c. And there we go. So we actually have our antiderivative of tangent squared x dx. This is an example of an integral that is basically solved using a manipulation, right? The integral, actually, the moment of integrating is easy. It just relies on realizing, oh, I know how to integrate secant squared, and I know how to integrate 1. But the trick relies on actually manipulating that integrand through this trigonometric identity to actually handle the integral. All right, last one here. We've got the integral of e to the x over e to the 2x plus 1 dx. Once again, this guy's a little tricky at the beginning because there doesn't look like there's much to do. This is an issue. Integrating quotients is always rough. Integrals do not play well with products and quotients. They distribute over addition and subtraction and constant multiplication. But whenever you see a quotient or a product, that's not particularly good for integrals because integrals do not distribute over that. You can't just integrate the top and bottom separately or anything like that. Well, there's sort of another sort of trick in terms of rewriting this. A nice sort of recognition here is that we can sort of rewrite this as e to the x over e to the x squared plus 1 dx. Now that doesn't change much, but it should be pretty clear, right? Power to a power you multiply, so that's where we're getting that 2x from. But by writing it like this, now it sort of resembles a composition. So let's try our U-substitution. So we're going to do a U-substitution. We're going to let u be e to the x. That means our du is going to be e to the x dx. Now notice, you can do it the way we did in part B, where I actually then take the time to write this over here as 1 over e to the x du is dx. Or you can actually just recognize, well, this right here matches exactly what I have here. So I can replace this entire e to the x dx with just a du. So again, doesn't matter which way you want to do it, but I just want to show you guys both ways because don't know how you guys saw it in 190. It probably all came from different classes. So let's just go ahead and try a different way of looking at it. So since this entire thing is going to be replaced with du, we can write it as 1 over, and then it'll be du now. Down here, well, we're substituting u equals e to the x, so it becomes u squared plus 1. So we have 1 over u squared plus 1 du. Now we can recognize this. That's actually we can integrate that as arctangent. So this becomes arctangent of u plus c. Whenever you finish your integration is the moment you put that constant of integration. Then we just pop our substitution back in, and we get that this is arctangent of e to the x plus C. So again, in both parts B and D here, we use U-substitution. I just wrote it out slightly differently. You guys are welcome to do U-substitution in whatever manner you sort of like, as long as it's sort of clear to follow. You'll also notice that in general, we're going to be doing a lot of integrals in this class, and I strongly recommend coming up with a nice sort of formatting of it. You'll notice that I really do like the sort of just vertical steps where each one is one sort of simple step. You know, from here to here to here is very easy to follow. The more steps that you guys show, the more partial credit that you can receive as I look over things in case there is an error, and it's just easier to sort of follow. It's also a good mathematical habit to put your sort of steps in small, manageable bites. So definitely as you're doing this, you know, not just focusing on always getting sort of just the right answer, but also in making sure you have a nice presentation of as you do your work here. All right, this wraps up our 190 review. There's some 190 review exercises that also talk a little bit about limits and things like that. You can take a look at those on your Canvas site. Our next video will actually move us into our real content for our course, which is section 6.1.